All right, let's take a look at page 141. We're going to continue to explore our x-intercepts today, and we're going to dive into different kinds of x-intercepts. Maybe you didn't realize that. Okay, there are different types of x-intercepts. And we're also going to take a look at a new graphical characteristic, not necessarily difficult, okay, just new. We're going to try to identify what's referred to as end behavior. So we're basically just looking at the ends of the graph and describing what the graph is doing. Now, when we describe it, we're going to use mathematical language. Okay, we're not just going to say up or down. Okay, we're going to do mathematical language. So we have three graphs that we're going to explore on this first page. We're going to start off with f of x, and they're telling us that it's a cubic function. It kind of has that S shape to it. So we know that the highest power is a 3. Cubic meaning 3. So if we're going to practice identifying the left end behavior, the right end behavior, if you look at the graph, what direction is the left side going towards? Down, yeah? Mathematically, negative infinity. Okay, so when we describe the left end behavior, if you're moving to the left on the graph, what are the x values doing? Decreasing, getting closer towards negative infinity. Okay, so on the left-hand side, the x's get close to negative infinity. And based off this particular graph, if we see the left-hand side going down, we also know the y values are getting close to negative infinity. So whenever you're describing end behavior, you need to have two comparisons. What are the x's doing? What are the y's doing? Same thing for right end behavior. If you go to the right side of a graph, what are the x's doing? Increasing forever, so positive infinity. And for this particular graph, notice how the right-hand side would be going up forever. So what are the y's approaching? Positive infinity. Okay. Now, if you just take a look at this first example, I do not want you to make the assumption that they're always going to be the same sign. It just happens to be that way for this example. Okay. Just for practice, can we find the zeros or x-intercepts of that graph? Good, Eli?
-2, -1, and 1.
Good. All right, let's try our next graph. G of x, they tell us, is quartic, like quarter. We're going to have a power of 4 as the highest power. Let's look at the left end behavior. So if we're going to the left, the x's are getting increasingly negative. Approaches negative infinity. Good. And based off of this graph, what are the y's approaching? Positive infinity. Okay, the left-hand side is going up. For the right end behavior, the x's would approach positive infinity because you're going to the right on a number line. And for this particular graph, what are the y values approaching? Positive infinity because the right-hand side is going up. So this is a good example. If you look at the left end behavior, notice how they have opposite signs. Okay, again, they will not always be the same. Okay, it all depends on what the graph is doing. What about the zeros for this graph? Can we list them? Roughly? Good, Lucas? Okay. And positive 2. Okay, I'd say negative 2.5 looks good. All right, h of x is a quintic function. So x to the 5th. Looking at the graph, the left-hand side is going down. So let's represent that mathematically. If we're going to the left, the x's get negative. And for this graph, if it's going down, the y values are also getting negative. For the right-hand side, the x's get positive. And for this particular graph, if it's going up, the y's are also getting positive. How are we doing with end behavior? Left and the right side? We're just looking for up and down, okay, basic characteristic. What about the zeros for this graph? Good, Eli?
-4, -2,
2, and what was the last one? 5. Okay, so we have quite a few for this one. Perfect. Okay, so we're going to spend the majority of today and tomorrow looking at these x-intercepts a little bit further. We have different types of x-intercepts. So if you take a look at all of these graphs, all of these black dots I've put on there are x-intercepts. But if you take a look at what the graph is doing at those spots, things start to change. And that's what we're going to explore. In order for us to explore that relationship, though, we have to get familiar with a new term or vocabulary word called multiplicity. Maybe you've heard of it before, maybe you haven't. But multiplicity, by definition, is the number of times an x-intercept is a factor, meaning how many times it goes in evenly. We get that remainder of 0. So we'll go ahead and jot that down. The number of times a 0 or x-intercept is a factor. And we kind of did a question like this yesterday. Do you remember the last question? How many times is it a factor? We had to go through division quite a few times to answer that. That's what we're going to be taking a closer look at in this section. Okay. Now, let's explore this relationship. I'm going to leave the page as it is right now because I want us to be able to see these graphs, but we're going to be reading the last few sentences at the bottom of that page. Okay? So if you look at the bottom, there is a sentence that says, the graph of f of x, all of the zeros have a multiplicity of 1. So they are only a factor one time. I'm going to go ahead and label all of these as 1, just so we can start to see a pattern. You don't have to do this every single time. I mean, if it helps, go ahead and do it. But we're going to start to see a pattern. The next line says, for the graph of g of x, the 0 of -2.5 had a multiplicity of 1, and the 0 of 2 had a multiplicity of 3. And the last line says, for the last graph, the zeros of -4, -2, and 5 have a multiplicity of 1. And for the 0 of 2, its multiplicity was 2. So based off those multiplicities, how many times they're a factor, can you find a connection with how the graph looks, how it behaves? You have an idea, Seth? Yeah.
Looks like the lines are closer to the zeros that have more multiplicity. It's like the one where 3 is, it's really close to that.
Like close to the origin?
Close to the x-axis, where that dot is.
That's actually on the x-axis. So these black dots. So when you mean closer, what do you mean by closer?
The line around it looks closer.
So around that spot, it's closer. Okay, so like this portion and this portion are closer. I like that. Okay, that's something we're going to look into. Are there any other connections? How do the graphs with a multiplicity of 1, or the zeros rather, how do the zeros with a multiplicity of 1 look? How does the 0 with a multiplicity of 2 look? How does the 0 with a multiplicity of 3 look? Can we find a connection? You see something, Eli?
Is it the multiplicity of 1, it always changes x from positive to negative, and then
Okay.
if it goes to 2, it stays on the same side, and then if it goes to 3, it flips back.
It changes?
It changes again.
Okay. When you say it changes negative to positive or positive to negative, what do you mean by that statement?
It flips the x-axis, like it crosses the x-axis.
It crosses the x-axis. Okay, that's what I was trying to get out of you. Good. So notice how all of these 1s, the graph goes straight through the x-axis. Can we see that? Straight through. Okay. The multiplicity of 2 does not go through the x-axis. How would you describe this? Touches, bounces, okay? So it doesn't go through it, it just touches it or bounces it. And then 3 is a little tricky, like Seth mentioned, around it. It's pretty close. We're going to classify a multiplicity of 3 as going through the x-axis, because clearly we go from below to above in this case. But as it goes through the x-axis, it starts to level. You kind of have that flatness to it. Okay, so we're going to go ahead and jot down those 3 descriptions on the next page. Those are 3 very important characteristics that we're going to be able to identify as soon as we look at a graph. All right, so on the next page, we're going to skip number 1. We're going to come back to another characteristic in a second. Look at number 2. If we have a 0 with a multiplicity of 1, okay, it's only a factor once, how did we say the graph should look? Or how should the graph behave? Graph goes across the x-axis. Okay, straight across or straight through. That word straight is pretty important. Okay, straight line. What if it had a multiplicity of 2? What was our description for that one? Go ahead, Eli.
The graph touches the x-axis, or bounces.
Touches / bounces, okay, off the x-axis, meaning it does not go through it. And what about the multiplicity of 3? Graph, good, Emma?
The graph goes through the x-axis, but it starts to level as it passes through.
That's very wordy. That's good. Okay, graph goes through x-axis. I have no idea if this is a word. Levelly? Works. Maybe we'll dictionary.com it later. Okay, graph goes through the x-axis levelly. So you are going through, but you're not going straight through. Okay, you start to curve and level and then go back up. Okay, so it goes through levelly.
So like a nail, like a nail like in the corner would, like if you would like put in a screwdriver, you know, for like a wood thing.
Mm-hmm.
That's what I'm trying to make it. I'm trying to make it like so that other people understand it. Like so, you know how there's like if you try to assemble a chair, there's always that insert hole where you put a nail or a screw and it's going like diagonally.
Diagonally. How would that make it? What do you mean by how would that make it level?
Like it goes in through the. Like the x-axis is like basically the one board you're trying to connect it. It goes through it like more diagonally than like it. Like
I'm trying to visualize it in my head.
Like a nail, other than like a nail going
straight through, yeah.
And then like the drill, the screw goes in like.
Goes that way, maybe. I'd have to see it. We might have a disconnect here. Okay. If you can show me a picture or like a video of that happening, maybe. Anyway, okay, let's go ahead. Let's go ahead and take a look at number 1. Okay, there's another connection that we want to make sure that we realize or notice with these multiplicities. Go ahead and take a look at the graphs again from the previous page. How many multiplicities did we have for f of x? 3. What was our type of function? Cubic. How many multiplicities did we have for the middle graph? What was our function? Quartic, 4. How many multiplicities? 5. Function? Quintic, power of 5. Coincidence? I think not. Okay, so the sum of the multiplicities equals, we'll say the highest power Okay? So if we can identify all of the multiplicities of the zeros, we can figure out what type of function it is. Quartic, quintic, quadratic, cubic, any of those. Now, there are other multiplicities out there. You could have a multiplicity of 4, 5, 6, 7, like anything's fair game. But as you start to get higher multiplicities, the behavior of the graph starts to be a little bit unclear. So we're only going to go up to a multiplicity of 3. Okay, we're going to stop at that point. So nothing should have something higher than 3. Does that make sense? Okay, so let's go ahead and explore these multiplicities a little bit more with these examples. With this first graph, let's go ahead and find the x-intercepts. We'll label them on the graph. And based off the way the graph looks, can you identify the multiplicity of each x-intercept? Yeah.
I think they're all ones.
They are all ones. Good. They all go straight through the x-axis. 1 plus 1 plus 1? 3. So our function is, can we name it? Cubic, power of 3. Good. Okay. So what we're going to do, we notice the multiplicity based off the graph. I know visually we can do that, but do me a favor, okay, humor me for a second. We're going to pretend that the graph is not there. Okay? So we'll cover it up. We're going to try to get the same result by hand. Okay, what if we didn't have a graph? How could we still figure out what the multiplicities were? So we're just going to do one factor as an example. Technically, we would have to do 3, but we're just going to do 1 to prove the point. If this is a factor of this particular polynomial, what would the related root or x-intercept be? If this equaled 0, it would give you -1. Okay, so by hand, we need to test how many times this -1 is a factor. How do you want to do that? How can we test to see how many times it goes in evenly? Synthetic division. Okay, so we'll let -1 be the outside number. And since we have the standard form equation, we'll use that to our advantage. Notice how all the powers are in order and nothing is missing. So we'll just write down the coefficients as they are. Again, we're pretending the graph is not there. Let's go through synthetic division. I think we're good with that. Is it a factor? Once, right? Let's check to see if it goes in again. So we're going to use the same -1 x-intercept, but this time we'll test the quotient numbers. We'll drop the first number and go through division. Is it a factor 2 times? No. Okay, so what's our multiplicity? 1. It's only a factor once. Okay? And notice how that checks out based off the graph, because we're looking at this x-intercept of -1. We don't have the graph. Okay, pretend it's not there. Based off of this result, multiplicity of 1, how can we describe the behavior at that spot? What do we know the graph is doing? Yeah?
Going straight through to x-axis.
Goes straight through. Goes straight through x-axis at x equals -1. If we look at the graph, that's exactly what it's doing. But notice how we were able to conclude that by hand using our synthetic division. Let's go ahead and try the next one. Graphically, we can find those x-intercepts. Looking at the graph, just for now, can we label the multiplicities based off how it looks?
-1.5
Okay.
is a 1.
Is a 1?
1 is 2.
Is a 2. Good.
That's so insane.
I know, right? 1 plus 2? 3. So we have a cubic function. Looks good. All right, let's go ahead and test this factor. If the factor is x minus 1, the x-intercept is +1. Good. All right, so synthetic division, let's test it. we're going to see how many times it's a factor. Is it a factor once? Yep. All right, let's test it again. Is it a factor twice?
Yep.
Yep. All right, let's test it again. Factor 3 times?
No.
No. All right, so multiplicity of 2. Pretend the graph isn't there. Okay, what's that result telling you about the behavior of the graph at this x-intercept? Yeah.
It is touching the x-axis or bouncing off of it.
Okay, so touches or bounces off x-axis at x equals 1, because that was the spot we were analyzing. Graphically, since we have the picture, notice how that makes sense. We doing okay? All right, let's try another one. All right, looking at the graph, we'll find the x-intercepts and classify the multiplicities. Go, Dalton. Is a what? 3. Thank you. Good. All right. 1 plus 3. 4. Type of function.
Quadratic.
Not quadratic. That's tricky. Quartic. Quadratic is 2. Little tricky. Quartic, like quarter. 4 quarters and $1. All right. So graphically, I think we're good because we have a picture. Let's pretend the graph is not there, and we're going to get the same result algebraically using our synthetic division. So we're specifically going to look at the factor x minus 1. The x-intercept would be positive 1. Let's see how this checks out. Did a factor once? Yep. All right, let's try it again. Factor twice? Yep. Let's go again. Factor 3 times? Yep. All right, now I told you we're stopping at 3, right? Okay, nothing more than 3, but it would be maybe in our best interest to just check it again to confirm that. Factor 4 times? Nope. Okay, so multiplicity of 3. Pretend the graph isn't there. How is the graph behaving at this x-intercept? What should the graph look like? Levelly. Okay, so goes through x-axis levelly. Okay, whatever phrasing you want to use. I still got to check to see if that's a word. Levelly at x equals 1. Doing okay? All right. We're going to save the rest of the section for tomorrow. I know there's still a little bit of time left, but I want to make sure that we can get it all done in its entirety because it's a little bit different concepts. Now, in the meantime, sophomores, most of us are not going to be here tomorrow, right? Okay. They're going on a field trip. We are having our partner quiz on Tuesday next week, which means Monday will be our free response day. So if you're not going to be here tomorrow, we're still going to go over the rest of this section. You need to get the notes from somebody or check out the video online, okay, from class. Deal? Okay. All right. You can use the rest of the period to work on some homework questions, ask for help if you need it. Otherwise, we'll pick up the rest tomorrow.